Students, I am going to discuss about paper layout gauging technique in this session. Shown here is a component having 4 holes. The size of the holes is 20.5 plus 00 plus 0.8. So the lower limit of the hole is 20.5. The upper limit of the hole is 21.3. Now, in order to control the position of the hole, a position tolerance 0.5 is assigned. So this position tolerance of 0.5 is applicable at the MMC size. The MMC size of the hole is 20.5 for this example. After manufacturing the necessary quantum of this sample as per the drawing, we have to inspect the samples. For inspecting the samples, we have to measure the size of the hole and size of the plate, and we have to check for the position of the holes also. If this component is going to be manufactured in mass quantity, we can make use of plug gauges for checking the size of the hole and functional gauge for checking the position of the hole. So the size of the hole, whether the hole is between 20.5 and 21.3, we can check using a plug gauge if it is going to be manufactured in mass quantities. And for checking the position of the hole, so this hole ought to be positioned within a tolerance of 0.5, within a position tolerance of 0.5 applicable at MMC. For checking the position of the hole, we can make use of the functional gauge. But making use of the plug gauge and functional gauge is applicable only when you produce this component in mass quantities. Suppose there is a requirement to manufacture this component only in 5 numbers or only in 10 number. So there is no need to manufacture this component beyond 10 number. In that case, using a functional gauge or using a plug gauge for checking only a 10 number of component is not practically feasible. For checking the sample, which are very few in number, we can make use of paper layout gauging technique that I am going to discuss now. After manufacturing the necessary number of sample, we have to measure the size of the hole using a vernier caliper or any other measuring method. Let us say the first sample is measured, and these are the dimensions of the first sample. This hole is 20.8. When we measure the hole size using a vernier caliper or any other measuring method, it measures 20.8, and this hole is measuring 20.7, and this hole is measuring 20.6, and this hole is measuring 20.5. After measuring the size of the hole using a vernier caliper or any other measuring method, I have to measure the axis also. I have to find the position of the axis with respect to the two surfaces, so the left edge and the bottom edge. So this hole, the axis of this hole is at 25.5 from the left edge and at 25 from the bottom edge. Similarly, the axis of all the 3 holes are measured, and it is recorded in this slide. So this is the second step we have to complete. Then, after measuring the sizes of the hole and the position of the axis of the individual holes, then we have to translate this measurement on a next transparent sheet. So this shows the axis of the hole are marked, and they are marked with reference to the two edges of the plate. See here, this hole is at 25.5. The axis of this hole is at 25.5 from the left edge, and from the bottom edge it is 25. It is marked there. Similarly, all the four axes are marked on a transparent sheet like this. So you can see on a transparent sheet, I am marking the axis of the four holes on a transparent sheet. Next, I am going to mark the applicable value of position tolerance in another transparent sheet. So the first hole, this hole is measuring 20.8. So this hole is measuring 20.8. The applicable value of position tolerance is 0.8. This hole is measuring 20.7. The applicable value of position tolerance is 0.7. So like that, in another sheet of paper, transparent sheet, I am marking the applicable value of position tolerance. So I am drawing a circle for a diameter of 0.8, which is the position tolerance for this hole. Similarly, I am drawing another circle for a diameter of 0.7, which is the applicable value of position tolerance for that hole axis. Okay, so in another transparent sheet, I am marking the applicable value of position tolerance at the true distance 100 by 100. So the 100 by 100 is the distance at which you have to locate the four tolerance zones for each of the four holes. So as you can see here, in another transparent sheet, okay, I am marking the tolerance zone applicable for each of the holes. Next thing is, I am going to overlap, okay, one sheet of paper with another sheet of paper. So one sheet of paper contain axis, another sheet of paper contain the tolerance zone. I am overlapping like this. Okay, I am taking this sheet, I am just overlapping like this. Okay, so both the sheets are superimposed one over the other to check whether the axes are lying within their respective tolerance zone. If all the four axes are lying within their tolerance zone, I can accept the component as far as its positions are concerned. Okay, if I am not able to bring any one axis, I can move the transparent sheet, okay, or I can move in the x direction or y direction, or I can able to rotate until I make it possible to bring the four axes, okay, within their respective tolerance zone. So if I am able to bring all these four axes okay, within their respective tolerance zone, the component can be passed in the inspection as far as the position of the holes are concerned. So this is called paper layout gauging technique, which we can use for checking for the position of the hole without making use of functional gauge. For inspecting very few components in the order of 5 to 10, we cannot make use of a functional gauge because of the cost. So we can make use of this paper layout gauging technique for inspecting very few components. But this technique has got some drawback. The first drawback is it is time consuming. For inspecting each and every sample, we have to make use of two transparent sheets, one containing the tolerance zone and one containing the axis of the hole. Like this, we have to prepare a set of transparent sheet for each sample. The second drawback is the accuracy of the inspection depends upon the accuracy with which we are making the sketch on the two transparent sheet. So the accuracy of inspection can be improved if you make use of any drafting software for making the two layer of the drawing. On one layer we can mark the axis of the hole, in another layer we can mark the tolerance zone in another layer. So there are some drafting packages available. We can make use of the drafting packages for improving the accuracy of the inspection using paper layout gauging technique. The transparent sheet that I used here for explaining the concept of papillary gauging is not drawn to the scale. As you can see here, I should have drawn a circle with a radius of, with a diameter of 0.8, with a diameter of 0.5, which is not possible when you draw the circle to the actual scale. If you try this in a drafting software, you can draw a scale, you can draw a circle even for a diameter of 0.5, 0.6, 0.7, 0.8. That way you can able to make use of the drafting software for verifying the position of the holes using the papillary gauging technique.